This is Math Studies Lesson 8.2, Counting Outcomes and Tree Diagrams. I have a couple definitions to start. The first one is independent events. Independent events do not affect each other. So think about like a coin flip. When you flip a coin, you have a 50% chance of getting a heads, a 50% chance of getting a tails. If you flip that coin again, it's still a 50% chance of one side, 50% chance of the other side. Each coin flip doesn't affect the next coin flip. Whereas a dependent event, that does affect the next. Events affect each other. And so that is best thought of as no replacement. So if I start with 5 reds and 5 blues in a bag of M&Ms, and I pull out a red M&M and I don't replace it, for my next event, there would only be 4 reds and 5 blues. So that's going to change the possible things in the bag. The multiplication rule for independent events is to find the probability of A and B, event A and event B. You would take the probability of event A and multiply it by the probability of event B. The multiplication rule for dependent events looks pretty much exactly the same. To get the probability of A and B, you will take the probability of A, but then you will multiply it by the probability of B given that A has happened. So that's what this line stands for, given that. So if I think about my 5 red, 5 blue M&M example, if I have 50% chance of getting a red right now, but I take a red out, then there would only be a 4 out of 9 chance to get a red, given that I took a red out. And I'll do a couple of examples that hopefully will make that a little bit clearer. But whenever we want the probability of something and something else, of 2 different events, basically we just need to multiply the probabilities together. So the first example, I have a tree diagram, and it asks me to find the probabilities, or find the values wherever I have a letter. I need to figure out the number, the probability that would go there. So off of each starting point, there's always going to be 100% of stuff happening. What I mean is this is technically an 80% chance of something happening. 0.8 is 80%. 0.2 is 20%. So that means there's a 20% chance of that thing not happening. Altogether, it's got to be 100%. So 80% and 20%, that's my 100%. So I can kind of figure out letter B the same way. This is a 75% chance of something happening. What's the chance that it does not happen? They have to add up to 100%. So 75% and 25%, that's going to give me the percent chance that the thing does not happen. And I'm going to show some work kind of how I figured that out. 1 minus 0.75, right? Because it's 100%, take away 75%, leaves me with 25%. I can kind of do the same thing for letter D. If I have a 10% chance of something not happening, the chance of that thing happening, again, it's got to make 100% altogether. That would be 90% or 0.9. If I want to get the chance of this thing happening and this thing happening, I'm going to go back to my multiplication rule up here. I'd take the probability of the first thing happening times the probability of the second thing happening. So to get the answer for A, that would be 80% times 75%. And you can just use those decimals in the calculator if you're not good with your multiplication, but I know that would be 60% or 0.6. So to get to letter C, we would take this 0.8 times this 0.25. And 80% times 25%. Oh, I didn't put that over here. 0.6. That would be 0.2, or 20%. And to get to letter E, we'll follow the path, multiply everything along the way. So 0.2 times 0.9. And I'll label that over here. And the last one to get to letter F, 0.2 times 0.1. So 20% times 10% is 2%. So I have these all written as decimals, but I've kind of been saying them as percentages also. But basically, off of the same starting point, we always have to add up to 100% or one whole. And to find the answers along the way, event A and event B, we always multiply those events together. Example B. Consider a bag containing 3 red marbles and 7 blue marbles. Create a tree diagram with probabilities showing outcomes when drawing 2 marbles with replacement. And it looks like part B of B, the only difference would be without replacement. So let's start with replacement. I'm going to start by saying I can either get a red marble or I can get a blue marble. So I'm going to label these red and blue. And right now, the chance of getting a red marble would be 3 out of 10, because there are 10 altogether if I add the 3 and the 7. So the chance of getting a blue would be 7 out of 10, 7 blues out of the 10 altogether. Now this says I'm drawing 2 marbles, so this representation shows that I either drew a red or a blue. I drew 1 marble. So I'm going to need a second level to show the second selection. So the second time I can either get a red or a blue again. And if I drew a blue first, on my second pull, I can again either get a red or a blue. Now these are independent probabilities because I was replacing those. So if I pulled a red the first time, I had a 3 out of 10 chance of doing that. I still have a 3 out of 10 chance. I didn't remove that red, I replaced it. This is an independent setup, so nothing changed. So that means the blue is still 7 out of 10, the red is still 3 out of 10, the blue is still 7 out of 10. And then as we saw on the first example, if I want the probability of a red and a red, I would just multiply the probability of red times the probability of red. So that's 3/10 times 3/10. I know that is 9%. So fraction, decimal percent, 9 out of 100, or 0.09, or 9%. The probability of getting a red and a blue would be red's probability times blue probability. So that's 3/10 times 7/10. I know that would be 21/100ths, or 21%, or 0.21, fraction, decimal percent, your choice. So then the chance of getting a blue then a red would be 7/10 times 3/10, which is again 21/100ths, or 21%, or 0.21. And blue, my bottom answer is 7/10 times 7/10. I know 7 times 7 is 49, so that'd be 49/100ths, or 49%, or 0.49. Now if I wanted to, I could check that all of these actually do add up to 100%. So I'm going to do that just for fun. 0.09 plus 0.21 plus 0.21 plus 0.49 is definitely one whole, which is 100%. So I've covered 100% of possibilities. Let's figure out what happens to my probabilities without replacement. My original setup is the same. Pulling a red, I have a 3 out of 10 chance. Pulling a blue, I have a 7 out of 10 chance. Now, without replacement means I'm going to take a red away, and now what happens? If I had 3 reds and 7 blues and I take a red away, I now have 2 reds and 7 blues, so that means the chance of getting a red would be 2 out of 9. And that's important because I took a red away, so there's only 2 reds, but because I took a red away, I took one from the total as well, so there's not 10 marbles anymore, now there's only 9. if I took that red out and now I'm looking at the chance of getting a blue, I still have 7 blues because I didn't take a blue away, but there are only 9 because I took a red away. So backing up so we can figure out what happens on the bottom here, let's say I took a blue out. So now my chance of getting a red, there's still 3 reds, but now there are 9 altogether because I took a blue away. And my chance of getting blue would be 6 blues left out of the 9 altogether. So the with replacement is my independent. None of my probabilities changed. But without replacement, now this is 2/9 is the probability of red given I took out a red. This 7/9 is the probability of blue given I took out a red. This 3/9 is the probability of red given I took out a blue, and then this 6/9 is the probability of blue given that I took out a blue. We're going to calculate the 4 answers at the end the same way as before. We'd be multiplying to get the probability of 2 red marbles. It would be 3/10 times 2/9. So if you are good with fractions, you can do 6 on top, 90 on the bottom, right? 3 times 2 is 6. 9 times 10 is 90. If you'd rather do percentages, that's 30% times, I don't know, 22%. If you would rather go with the fractions, you can do 3/10 times 2/9, and it should give you, I think that's right, 6 out of 90. Yeah, so this calculator kind of does it the same way. So I can give 6 out of 90 for the fraction. I can say 0.06 repeating for the decimal, or I could say 6.6%. I'm gonna go decimal. So if I do 3/10 times 7/9, that would be 21/90. And that would be 0.23 repeating. So basically 23%. This is going to be the same outcome because 3 times 7 on the top would be 21, 90 on the bottom, 21/90. And then my bottom one, I would do 7 times 6 is 42 out of 90, and that would be 46 with the 6 repeating, so about 47%. So we can compare with versus without replacement. Looks like my probabilities of 2 reds and 2 blues both went down by about 3%, but my probabilities of 1 red, 1 blue each went up by about 2%. I believe that's it for these notes. Good luck on the exercises, and please let me know if you have any questions.